Thanks very much.
Okay, so I started the recording. I think it should, yeah, now it's on. So hello, and let me welcome you to our webinar, which is kind of a mixed webinar between digitalization and the energy sector, because we are looking into how the digital tools can help to save energy, especially for small and medium enterprises and current households. Well, the idea behind this webinar is quite clear because the energy cost in all the Europe and all the rest of the world are getting higher and higher. Some countries are really struck with this energetic crisis, we can say, and a lot of small and medium companies which didn't seeing it as an issue, the energy cost. And now it's really existential for them, and we are going to look how to tackle this problem and how to find some solutions which will provide the production with better efficiency. For this, I have our expert Erik Odvářka, which he will introduce himself, but he's the expert in this topic, and now I'm giving the word to you, Erik.
Thank you indeed for your kind words, Martin, and I'm very pleased to conduct this webinar with you today. And just to underpin what Martin said in terms of the sheer impact of increased energy prices, I recently conducted a LinkedIn survey throughout the community of my followers, who number nearly 2,000 in terms of management, primarily management staff of the companies based primarily here in Czech Republic. And more than 80% of the votes suggested that the annual price increase for the energies was above 100% between 2021 and 2022. So this is just to underline what impact it has caused to the companies, and especially if the company operates as some sort of tier supplier in the supply chain and might run on relatively low gross margins. You can imagine what is the impact to the company financials.
Yeah, the impact can be a little bit different throughout the countries, but especially in Czech Republic here, we can see the huge impact on the production.
Well, and now let's turn to my introduction. I'm a founder of a small consultancy, DigiPlant, that deals with engineering and process design primarily. So we helped primarily small and medium-sized enterprises to actually lay out, deploy, and optimize sort of the key value-adding business processes in terms of how to organize the supply chains, manufacturing, and first and foremost, the energy flows within the enterprise, so that the companies actually improve their performance in terms of the KPIs. So we tend to do measurable stuff. And we also help the companies to implement the change projects that we identify within the discovery phase. So in terms of the case studies we've recently conducted, very interesting project was in a company that deals with thermal processing of metals, where we significantly improved upon costing and saved quite a bit of energy. And we will discuss it on forthcoming slides. Other examples would be how to increase OEE, overall equipment effectiveness of the production lines, shortening lead times, so making sure that the production churns out what it needs to churn out more efficiently when it comes to repeated mass production. Or another case would be that we prepare and help to implement planning and scheduling for production with subsequent deployment of manufacturing execution systems and advanced planning and scheduling systems. So speaking of myself, In terms of my trade, I'm an energy engineer oriented on electrical engineering. However, I do have a professional experience from aerospace, automotive, as well as energy machinery. So imagine the large generators and stuff like that. From research and development down to production support and field support. So it kind of gave me a good overview. What needs to be addressed at what phase of the product lifetime. And then I also have an experience from software side in terms of application development and driving large portfolio of ERP projects in SAP and Oracle for Dow Jones Industrial 30 listed major international corporate. And then I decided to actually go on my own, set up a DigiPlant, and currently I help mainly Czech companies, but occasionally I also spread my services abroad. And in a free time, alongside with spending time with my lady, I do lots of gardening, home energy. So these topics somehow underline and cross my day-to-day routine overall. So the first subject I would like to touch upon is how to work and how to choose the energy source mix. And it's a big subject. So you might recall that the Germany rolled out the Energiewende, as they'll call it, sort of 10 years ago, meaning that the influx of renewable energy resources was supposed to be complemented by natural gas. Now the natural gas supplies are not that straightforward because of the geopolitical climate, and the prices have gone up. And somehow the Energiewende kind of hit the wall by its head, how to go forward. And you can use this analogy in operations of a company and also in terms of how to run your household. So the question you might ask is it worth to keep a gas boiler? And there are countries that actually plan to disregard further installation of gas boilers going forward. But how does it work? If you have a gas boiler in your house and you can operate a heat pump in parallel, and let me point out that this is the way I configured my family house where we live, and you can take it away to lots of small and medium-sized enterprises. And on the bottom left, you can see how these energy resources can be complemented. So you got the blow curve, which is the building power loss. So lower is the ambient temperature, inherently more of a power you need to deliver so that you maintain constant indoor temperature of your dwelling. And interestingly enough, the green curve that actually trails a bit behind. And that's because the condensing natural gas stoves or boilers, actually, if you count in also the condensing specific heat of the condensation, have efficiency above 100%. If you refer to the boiling heat, it can actually release. So that's why it's a bit below. And then you can look into what does your heat pump does. You see that gray curve at the bottom. So if you start from the right to the left, a bit contradictory, but if you start at 20 degrees ambient temperature, you see that the gray curve steadily increases somewhere to the region of -8 degrees C. And that's the threshold where most of the heat pumps actually do not yield more of a thermal power on the output referred to the electrical power that you put in. And you have to start complement it by a backup typically electrical capsule that converts electrical energy into a heat. So you see that the overall consumption starts shooting up, and it somehow starts converging with the natural gas. So there is a threshold that it's actually effective to use the heat pumps. But if you are in the Nordic regions in particular, and I believe we have guests from Finland, potential listeners from Finland, it's definitely not a good idea to get rid of either a gas boiler or perhaps a wood stove or some sort of another resource alongside with the heat pump. And I've done a bit of an analysis in terms of Czech energy prices. So a typical household or small medium enterprise would purchase per the governmental price caps the electrical energy per 6 crowns per kilowatt hour, and the natural gas would be considered at 3 crowns per kilowatt hour. So you would have to basically the natural gas cost would have to drop to 1.8 crowns per kilowatt hour, so that it would be effective for you to switch it from a heat pump at 0 degree ambient to the gas boiler, and vice versa. The electrical energy would have to rise up to 9 crowns per kilowatt hour, so that again it's effective with the fixed gas price to switch at 0 degree C. So it actually tells you that the heat pump is still very robust and insensitive to relatively small price volatility to the input energy commodity when it comes to the temperatures slightly below 0 degree C. And I've touched upon Energiewende, and perhaps it's worth to recap how the energy prices actually how they project from the European markets. So the prices per 1 megawatt of electrical energy, so that's the raw power that is traded on the international market, on the energy market, especially in Leipzig in Germany. So it hit the bottom at below 50 euros per megawatt hour back in 2020. So it was actually before the war began. But already back at that point, the Germans started decommissioning the nuclear power stations. So lots of these legacy power stations were decommissioned, not only the nuclear, but also the coal-fired. Yeah. Yes, exactly. So it started becoming apparent that there won't be sufficient supply of power from these stable power stations that you can operate all year round, because the renewable energy resources do have lots of volatility. Wind and solar somehow complements in terms of how they yield in terms of daytime and also seasonally, but we might get actually periods when the wind is insufficient, even during the winter time and overnight. And suddenly you need to have readily available reserve power. So that is typically hydropower, but you cannot build in Europe somehow a lot more of these massive hydro installations. And the assumption was that it would be complemented by the natural gas. So then the electrical energy shot above 200 euros per megawatt hour when the war began last year. And it is anticipated that it will settle somewhere around 100 euros per megawatt hour in foreseeable future. But it's difficult to anticipate what will be the demand for the LNG worldwide. And should the demand for LNG increase, then Europe will have to start purchasing on the spot market the relatively expensive LNG, and it may not stay at the 100 euros per megawatt hour. But in any case,
even higher.
Yeah, it might go up again, especially as China recovers and the Southeastern Asia is very energy hungry after all. So there is a risk of continued volatility in prices. Let's put it this way. And if you draw a conclusion, the spot market was 40, 50 euros 3 years ago. Now it's 100 plus. So you see 2 to 3 times increase in any case, even if we consider that optimistic scenario going forward. And if you look at the electricity bill breakdown, that is typical in Czech Republic before the war began, typically half of the amount the end user paid was accounted for the purchase of actual energy on the Leipzig market, and the another half was associated for the subsidies for renewables and for the distribution fees, etc. So it was like half and half. Now the gross power that you purchase in the market is becoming more significant. So the takeaway from this slide, definitely try to keep plurality of energy resources to both temper your house and to provide energy, should it be thermal energy, electrical energy, if you can, for your small and medium-sized enterprise. And the same applies to the technological process. Lots of technological processes could be run leveraging electricity or natural gas, especially when some sort of heat processing is involved. So if you can maintain both, because there might be lots of volatility in the energy prices going forward, and also volatility in terms of sufficiency of supply.
So the main problem here is that if we are using, for example, the heat pump, the efficiency can rapidly change with the ambient temperature.
Exactly.
And that's why I need different sources which I can switch when the efficiency of the heat pump will go down. I will start with the natural gas or coal, or I don't know, something else.
Or wood, yeah, whatever is. Yeah, so for case of Finland, the wood pellets might be very plausible substitute for heat pumps. But as you, Martin, pointed out, for instance, to leverage a heat pump in a summer season or late spring when you still need to supply domestic hot water, the heat pump is fantastic because you can operate it with the coefficient of performance 4:1. So that means for 4 kilowatt hours of heat you draw out of the heat pump, you can deliver just 1 kilowatt hour of electrical power. So it's fantastic.
All right.
Okay, so let's move on. Let me discuss a bit more on the aspect of heat pump operation. So the heat pump, you can perhaps ask the supplier next door to install it to your house or to your small and medium-sized enterprise, because still you need to heat the enterprise, or you might need to provide cooling in summer. So heat pump, again, modern heat pump can not only deliver heat, but also cold. So that's, I think, applicable a lot to Italy, for instance, as we have a guest from Italy here. But typically, you would get the heat pump installed with the bare minimum accessories. So on the bottom right picture, right in the middle, I will hover there with my mouse, you would see the circulation pump. And perhaps you would have a pressure gauge that actually looks at whether you got sufficient pressure in the heating system as such. But you would hardly have any means how to actually assess how your heat pump performs. And there are also multiple means how you can address it. But there's a very straightforward approach you can take, so that you ask the heat pump installation company to install also the calorimeter or the power flow meter, if you like. That's the white box in the bottom right picture on the right-hand side, and it actually measures the temperature difference between the inflow and outflow pipes of your heating systems. So it obtains the delta T between the temperatures. It knows that you circulate water in the system, so it knows the specific capacity of the water, and it measures also the flow of the water, and it calculates hence the actual heat that the heat pump delivered. And we will elaborate how does it compare to the data sheet, and it's quite interesting reading, you will discover. And then a simple device here on the left bottom part in the middle. It's a single frequency smart meter on electricity, and it's actually a very cool device. It measures the power factor that draws the heat pump, the actual electrical power, and also it checks on your grid frequency and stuff like that. Very cool. So if you need evidence that you need a UPS to back up your system, it tells you that, and it costs peanuts. It costs 50 euros. It's actually incredible. So you can get all this kit just for 400 euros. And it's a basic kit that connects via Wi-Fi to the smart home app. And you can plug the heat pump. You can plug any kind of significant energy consumers, such as fridges and washers and dryers, and you can start controlling your home. It's actually quite fantastic. And you can start scheduling the loads so that you smoothen the consumption, or you leverage, for instance, the excess power you produce by your photovoltaics. So it's actually very cool to start building up your smart home using these very affordable devices, and to actually install all these measurement kits. It just costed 400 euros or 10,000 crowns. So if you consider that in Czech Republic, a decent heat pump with the installation costs you 400,000, it's very marginal investment, and it gives you lots of data. So essentially, you start understanding, okay, I have the room thermostat, and I can understand what is happening indoor. You can buy a meteor station, again, for 100 euros easily, that connects to your Wi-Fi app, and you can start getting a feel of what the ambient does and what is the forecast, etc. And you get these devices. I should have mentioned also the ball valve that actually hosts the temperature sensor on the other pipe. And you start building up the integration platform. And it is a pretty neat step, because for low investment, you start understanding when you should run your appliances so that you get maximum efficiency out of it.
And this is actually, you can use it also in the small and medium companies.
Absolutely.
And you were saying that if we are monitoring the efficiency, if the heat pump, it will be different than in the data sheet, and you will be surprised. So what's the finding you measured?
Yeah, so I'll turn on the next slide.
All right.
And this is actually a real data set that was measured this year in January and February on actually a very up-to-date heat pump using R290 coolant. So R290 coolant is essentially a new mandate that came from the European Commission, because unlike some of the legacy coolants, it has got absolutely minimum impact on greenhouse emissions. So you might know that not only CO2 but also methane is a big greenhouse gas, and so as lots of the legacy heat pumps have a coolant that contributes significantly to the global warming. So this is a very up-to-date type of a heat pump, and we started measuring what actually the COP does, the coefficient of performance. So what you can read out of this data is what was the ambient temperature during the period. So as you can see, the very bottom was -13, so not favorable at all. You can see that the COP was just down to 2.2. So we had to deliver 1 kilowatt hour of electrical energy to draw 2.2 kilowatt hours of heat. On the other side, you can see that we've gone up even above 3 COP. So you cannot see the exact trend because it depends on what the heat pump does. The heat pump also performs so-called defrost. So especially when you run around and below freezing point, because the evaporator actually extracts the heat from the ambient, it starts developing an ice on the evaporator. And you may see lots of heat pumps failing because they do not perform the defrosting. Excuse me, they do not perform the defrosting properly, and then the heat pump can go actually in a failure. So it's important to actually check that the heat pump performs that, but essentially it decreases the actual coefficient of performance, because the heat you would have otherwise delivered to the dwelling or to your plant, you have to use for actually de-icing, defrosting the evaporator. But you can see that there's a big variance versus the data sheet. And ironically, it was at -13 ambient, so the already unfavorable condition, where the actual COP was 2.2, it should have been 2.8 according to the data sheet. So you can see that, you know, it's good to understand how the heat pump actually behaves in real case scenario. The variance might be also because of the variation on the actual water temperature that's circulated in the heating system. If you set the heating temperature up in terms of the water, it decreases the performance. So lots of tuning, but it tells you that essentially you have to take the data sheets with a grain of salt, to put it mildly. But anyway, the key takeaway is, if you think of a typical day when you operate the heat pump and you want to gain maximum out of it, you know, from the previous slide, you understood that lower is the temperature of the ambient and greater is the set point temperature of the water circulating in your system. Worse is going to be the coefficient of performance. And just an illustration, you know, if you think of a household that has got 4 inhabitants, and you would consider that the heat pump provides the domestic hot water. If you assume each person consumes 50 liters per day, so the total requirement would be 200 liters per day for that household. And you assume that the water needs to be heated up compared to the freshwater inlet from 5 degrees C to 45. That means the temperature gradient is 40 degrees C. You would have to deliver roughly 10 kilowatt hours of energy to the domestic heat water reservoir every day. And just for comparison, if you set the controller so that it heats up that water early in the afternoon, say on a typical winter day in our latitude, longitude, the ambient would be 3 degrees C above zero. The heating factor 3.7, you would consume 2.7 kilowatt hours. If you let the heat pump operate in the night or in early morning when the temperature typically hits the bottom for the particular day, so let's think of -5, you already talk about 3.2 kilowatt hours of electrical energy. So just by this simple programming step or configuration step of your control unit on the heat pump, you can save 0.2 kilowatt hours every day, just on domestic heat water, which annualizes at 1,000 crowns every day. That remains on your family budget.
That's approximately 40 to 50 euro. But if we are also talking about the small and medium enterprises, where in the production, where the
Exactly.
energy consumption is way higher, so it will bring the way higher spendings, savings. Yeah.
So basically, you can think of it as a methodology, and it gives you illustration. You can scale up the numbers for your particular use case, and the same applies in terms of cooling. If you open a data sheet of a heat pump, it gives you also the performance data for cooling circumstances. And important to say, when it comes to management of heating or cooling, the buildings have got significant thermal inertia or thermal constant, if you like. You know, you don't have to pump the heat or cold constantly at any given time. You can leverage if you do perhaps spot trading, if you produce energy using your photovoltaics. Bingo, you know, it's a sunny Italian spring day. The photovoltaics has got massive yield. You know, let's leverage. Let's heat up the hot water storage. Let's accumulate cold in the building. It's totally fine because the thermal constant is great for the buildings, and you don't have to pump the heat or the cold constantly in any given time, but you can allow a bit of a swing of the temperature so that it is not bound to maintain constant 21 degrees C inside temperature with tolerance of 0.1. But if you let an interval of 20 to 22, somehow the control system can start leveraging more effectively that okay, the outside temperature, the ambient temperature is favorable. So I start producing cold or heat, whatever is the medium, and I leverage the favorable conditions. And there are lots of systems that actually enable you nowadays to start setting these control rules. But first and foremost, start measuring, start understanding how the installations behave, what the building actually behaves like, and then you can start saving through the efficiency. So what you see in the datasheet, in other words, that's the prime scenario. The heat pump doesn't perform defrost. It is relatively dry air outside. It doesn't condense too much of water that would freeze into ice. Okay, it yields you these significant power factors or coefficients of performance, I should have said. But in real operation, it could be significantly detrimental to what you see in the datasheet. Another example actually touches upon a small and medium-sized enterprise that I had the opportunity to consult with. They had a need of low potential, hot domestic water. Often in these scenarios, the households and enterprises would use natural gas. But think of the company that I would like to illustrate over here. So they produce consumer products, and they need roughly 2 cubic meters of a warm water at 40 degrees C to dissolve powders into liquids. And they do just extended day shift. So they run the operations 10 hours daily, approximately. So the requirement was so that we are at any given point of time able to release up to 1.2 cubic meters of that hot water that have to be heated back to the reference set point in 2 hours again. So in the current state, they used a electrical boiler, so just pure electrical energy to heat conversion. So we calculated what it would take to actually size a heat pump. This requirement to heat up that water tank in 2 hours is quite aggressive. You would probably be okay with doubling that time, and still they would be able to perform the operations, but they plan to expand. So we said, okay, so let's leave you with a contingency at the end of this project. And by doing that countermeasure, the company can save 90,000 Czech crowns just on replacing this single electrical boiler.
Which is approximately 4,000 euros.
Exactly, 4,000 just on energy that is used to dissolve these powders. And what we did for that company, was okay. So let's look forward. And they use these fan coils that you see on that diagram at the logistics and warehouse hall, and also in the production shop floor. And essentially what it does, it has got a central source of hot water. In that case, it is again a natural gas boiler. So we said, okay, let's start planning so that in the future, you will effectively paralyze these heat pumps, and you would be able to use, again, in the favorable conditions, the hot water from these heat pumps so that you can discharge that heat into the shop floors using these fan coils. So they don't care what is the energy source. They need energy. So the go forward plan is that they will maintain also the gas boilers, but in future, these gas boilers would serve again as a backup and complementary resource when the temperature starts dropping significantly below 0 degrees centigrade. So importantly, you can start planning the projects so that you gradually build in these renewable energy resources and use them in the favorable operational envelope. So do not treat it dogmatically that I have to get rid of my gas boilers immediately because there's going to be lack of gas or whatever. You can buy even a buffer tank for natural gas. There are multiple means what you can do, but think about how to make your company resilient. Before we started this show, I mentioned, Martin, that Czechoslovakia and then Czech Republic actually were, over the last multiple decades, net exporter of electrical energy. Even a few years ago, Czech Republic exported 10% of annual production of electrical energy into the neighboring countries, helping Austria and Germany predominantly. According to the last report of ČEPS, the ČEPS is the national grid operator that actually operates the transmission grids operating at the very high voltage levels, 220 kV and 400 kV. So that's the maximum level we use in Czech Republic for power transmission. So according to the report, already, and now I repeat, a few years ago, we exported 10% net of electrical output. In 3 years' time, we are going to start importing, especially in winter season. But now, having said that the Germany got rid of the stable power sources, there is no supplement. Austria is lacking energy for the last 30 years at least. Poland is decarbonizing. Now the energy safety comes in place. Right? I think it's needless to comment in more. And that's more or less across the Europe.
So the demand for energy is it going higher, but the production is
the demand might not go higher, but the trouble is instability of supplies, because most of the new resources have got volatility associated with the supply curve.
Ambient temperature, the sun,
the wind speed, etc. But we lack stability, and the stability was supposed to be provided by the combined gas-fired plants, the cogeneration units, as well as by the hydro, but there is clear lack of it. The static energy accumulators based on lithium ion, you can imagine that these are super expensive, and you are fortunate to install several megawatts here and there. So that needs to pick up. Lots of pace to be able to catch up with this demand for the short-term energy peaks. So this is just to underline why it's good to think about having the backup means in terms of different energy sources. So I've touched upon the energy security, and I hear lots of comments from the businesses when I discuss with them energy mix in terms of how to complement the energy resources, when we discuss energy safety. And frequently I hear, we have installed photovoltaics and we are fine. So I mentioned, okay, but looking at the last winter data, there were days in December 2022 when the solar installed plants here in Czech Republic operated at 2% of the net capacity, 2% only, right? So it tells you how volatile are the supplies for the photovoltaics. And on the left-hand side, you see a medium-sized enterprise. Is none of these big iron works we have still here in our region, but as a medium-sized enterprise, according to the EU categorization, that consumes 6 gigawatt hours of electrical energy annually. Excuse me. And they've installed, and I've used exclamation marks because it's a very big plant that has got a peak production capacity of above 400 kilowatts. It's very significant. And the annual yield is also significant, approximately 400 megawatt hours. We are a bit north. The climate here is a bit more cloudy and rainy than compared to, for instance, the South Moravia. In the south part of Czech Republic, you would get 10 to 15% more, just for comparison. Not speaking of Italy, that's totally different ballgame. But the situation in Finland is again going to be a lot worse because of the lot greater latitude. And you can see at the bottom that even in the summer months, there is no chance that the solar power plant, despite big installed capacity, will by any means ensure self-sufficiency of that operation. So in that case, it's about lowering the bills. There was a good business case because they were able to draw also 50% subsidy from the government, from the recovery fund, the National Recovery, the NPO, as we call it here. However, the other company, there was the company where we dimensioned the heat pumps so that they produce the water for dissolving the powders. There was a very different story because it's energy very little intense type of operations. It's basically producing consumer goods. So they do not have except of handful of compressors and some few small devices, any major technological energy need, except of that hot water. And as you can see, that company is able to produce significant excess power, especially in the summer month. It's a relatively small business, so they also ramp down a bit in the summer period, in July and August, when it is the season of holiday break here in the country. So suddenly it's a different game. There's somehow a love brand here in Czech Republic in some aspects. So it's very handy that we can depict this company as environmentally very friendly. And as you can see from the data, by no means it is a green painting. This company actually does produce surplus power. And as you will see on further slides, we started discussing how to leverage it in the short range expedition and logistics, because they do have lots of customers and they supply warehouses for further distributions locally. So we said, okay, this is a particular scenario. We calculated that they can supply on an average month in a summer period, couple of company fleets and a electrical van. They have a demand that they need to haul a ton, and typical van can actually carry like 1.25 of a ton. So it was a perfect scenario. So we said, okay, in the investment plan, we are gonna purchase a couple of EVs, one hybrid, because the CEO actually commutes from a longer distance. So it's effective to have a hybrid. And then the local supply, so the distribution warehouse, and to the local customers is going to be conducted electrically. And this company is going to actually leverage its own produced electrical energy throughout the summertime. So very happy scenario for this company. But what I want to point out is that it's very mindful to conduct an analysis of what the individual renewable resources can do for you and how you can complement these resources together. Indeed, the company, the light operations on one hand side, is going to drive the heat pumps that they will install using their own photovoltaics power. So it's a fantastic story. So it's a lot about systems engineering. Try to seek, what kind of energy media you need to use in your company, and if you produce anything excess, how it can help your logistics, how it can cover your transport demand. So lots can be done. And this company, as you can see from the picture, is also in a position so that they can use static energy storage to cover the need for nighttime. Operations is basically about making sure that there's some basic lighting, the servers are running, and they can happily use static energy storage to cover that. So very good success story, in my opinion.
So for the summer, it's photovoltaics and the heat pump,
right?
And for the winter is LNG.
So in that case, they are still fine to use the grid supplied natural gas, but you are right. You know, they can. Well, you cannot buy that easily LNG as such, but you can buy, for instance, the LPG, the liquefied propane, that can be supplied to the small end customers such as this one. And I've elaborated a bit upon you know, the choice of electric vehicle or diesel. You know, Czechs love diesel cars. You know, like roughly more than half of cars are sold with diesel. So, you know, I thought to illustrate what does it mean if a company decides to switch. And again, for lots of use cases, and the company I discussed on the previous slide is a fantastic example of that. You know, it makes full sense to switch to EVs, especially when the duty cycle is convenient. So the typical electrical car consumes 18 kilowatt hours of electrical energy per 100 kilometers. So if you use the current electricity price caps imposed by government, it would cost you 108 crowns per 100 kilometers. If you use the fast charger over the highway, the electricity tends to be more expensive. So roughly 10 crowns per kilowatt hour. So you would need for your average duty cycle 180 crowns, a bit more expensive. But if you compare it with a energy efficient, you know, diesel that consumes 5 liters per 100 kilometers, that will cost you the current prices comparable to the fast charging on the highway. So, as we discussed the previous company, since they do lots of deliveries around the location, they're actually located near Brno, which is the second biggest city in the country. There are lots of distribution warehouses around, so very kind of logistically convenient location. So again, it makes sense also economically, so that the company switches for the short haul journeys where you can use the inbuilt energy storage of the vehicle, and you don't have to stop at the gas stations to use the fast charging. So it yields actually a benefit to use the own power. And if you make it from the photovoltaics, you save even more, right? Because it kind of, once you install it, it comes for free.
You already have that energy.
Yeah, exactly. You know, so it's actually encouraging. And again, you know, if you think about it rationally, use these EVs for the short journeys. If you organize your logistics so that you can leverage the short journeys, and you can make the journey with the vans, perhaps with the small lorries in the future, so that you can charge it at your property. You know, it actually makes a return. It's fantastic.
But again, there is the difference that in summer you have surplus of energy, you have a lot of energy, so you can have the electric vehicle fleet. But in the winter, that could be a problem.
That could be a problem in the future, because I recall German government actually discussed over the winter time that there might be a need to slow down the pace of charging, meaning that the charges would be restricted on the power that can transmit to the vehicle energy storages. So I think it's going to be heavily influenced by how much of actual power will be available in the winter time. But still, Martin, if you look at the figures, I did the calculation for 6 crowns per kilowatt hour. So the price cap, you cannot pay more in Czech Republic in current circumstances. So even if you use the worst case scenario in winter, assuming that the power will be available and the grid operators will not impose any caps on the power drawn by the EVs, which might happen in the future, in the winter, depends. Still, it makes sense in terms of the returns.
Yeah, it's still comparable to.
Yes, absolutely. Yeah. So I think that's quite encouraging, and I trust since we prepare this show for small and medium-sized enterprises, and I trust you are cost conscious, because the small businesses have to be very careful about where they invest their funds. So it is a very encouraging sign, and for our listener from Italy, the figures would be even a lot better. So now I will start moving more towards the plant operations. And a big opportunity that I see that it hasn't been leveraged in many companies is so that nowadays there are widespread and cost-affordable systems of either machine supervision or so-called manufacturing execution systems. So the machine supervision system, what it does, it basically measures what your machines do. And in plant operations, it's actually very handy because before you can start planning effectively your manufacturing operations, and now I speak from my other background of process optimization, you need to start understanding what is actually happening in your shop floor. And especially the smaller and medium-sized enterprises I work with, I heard lots of stories about when asking, so what is your overall equipment effectiveness? And that OEE, that is very frequently spelled in the industry, it decomposes of three components. It is disponibility of your devices. So how available are your devices? So it's like a unitless measure, but if you plan for 2 shifts working week, so that means you got 10 shifts a week. So your planning capacity might be up to 80 hours per week. And if you say my availability was 72 hours out of these 80, meaning that the remaining 8 hours were downtime. For instance, the machines were in some state of repair, or there was some kind of partial breakdown and they couldn't operate at a full throughput, you would have OEE component availability 8 at 90%, 72 out of 80 hours. And the automotive standard, the automotive plants are typically the most fine-tuned in terms of availability, power, and quality. They can get up to 85% of OEE. And I visit the typical small or medium-sized enterprise, and I hear, well, we've got OEE 70% at least, and we are fine. I say, okay. But I encourage you, let's start with the machine supervision system, and we quickly discover that they're lucky if they have 40%. Right? That's very common.
There's a difference, 40 and 70.
Yes, because they frequently do not have the data. And since we speak about energies, you can see that's a bit chaotic on a first appearance graph on the right-hand side. But what it tells you, it is actually a snapshot from one of these machine supervision systems. And the cost-affordable systems actually work so that you put current measurement probes on the terminals of the machine, and the signal processing unit is actually calibrated so that if the machine performs actual manufacturing operation, the consumed current should be within a certain range. So that's the higher value that it oscillates. Because if it's some kind of machine tool, it pushes harder, then it eases off. So it cannot be constant power drawn by all means. And then you see the second phase is significantly lower, but that's when the machine is actually active, meaning it's turned on.
It's on standby.
It's standby, exactly. Yeah. Thank you, Martin. So it is available, but it doesn't yield anything productive. So that's the second component of OEE. I have available machine, but it doesn't have any throughput. Yeah. Interestingly enough, even when the machine sits standby, and you can see the snapshots from 2 different machines, easily 10% of a nominal power is consumed in the idle mode. And what we do with my customers frequently nowadays is that we start actually installing these small boxes that would cost you several hundreds of euros, at the most up to 1,000 euros. And if you have machines that operate frequently and you are doubtful what is happening on the machine, I very much encourage you to install these, because then you see whether how much the machine is actually available. And out of that available time, what percentage of time it actually yields something productive. Not only you can start working with your operators, how to make them more efficient, because you can start drilling down. So why the machine was actually unavailable? Was it a failure, or you lacked proper tooling, or there was a error in bombs and routings, and hence you were confused what to do actually, or the internal logistics didn't do their job and you didn't have a material or semi-finished goods or the inputs that you needed. So it helps you to improve the operations, but importantly, it also helps you to understand the true costs. So the conventional routing would have consisted of, okay, here are the steps I need to perform to finish my goods. Here's the bill of materials. So it tells me what kind of materials and semi-finished goods I need in what quantities at what step. But I'm telling my customers, especially if they perform heat treatment operations, they mold plastics, they machine something, start machining energy, electrical energy, because the price will remain high. It is not as it used to be, like 3% fixed cost element in your overall cost structure that you can just dispense across the company, but start understanding what each of these steps cost you in terms of energy as well. It is not only about cost of material, cost of labor, but also cost of energy.
I heard that it's a big issue, especially for small and medium companies, that they didn't think about the energy cost before.
Right.
And so they actually don't know what energy cost or power they need for certain products.
Exactly.
So when the price for energy will change, so will the production cost, and they don't know what products should cost more,
Right.
and what.
Right.
So this is something you also
yes
experienced.
We've experienced it, and I have a pretty interesting slide covering that subject. What happens if you leverage your manufacturing technology in an efficient way? For instance, you might have not a mass production, but sort of a small batch type of production, or piece by piece type of production, individual pieces. So you have lots of downtime because of you need to retool, you need to adjust. The machines actually spend lots of time in this idle mode. So all of that costs you, and the companies typically do not track it, and hence they do not understand that in terms of the cost structure, as you pointed out, okay, I have lots of downtime. When we actually change from product A to product B, so it's not only about the cost of the downtime in terms of the labor, but also because of the energy that idles. And when we produce, we don't understand how much of energy we've spent. And it happens frequently that the companies do not think about how to size the batch per the production order so that you leverage your technology. And we will discuss it on the one of the follow-up slides. What it means that if you do not leverage your device in terms of the optimal batch volume, if you like. So then your cost structure is basically very inaccurate, and the company loses the margin, and that's important. There is a big pressure on margin coming from every side, not only in automotive, but in all sorts of manufacturing segments. The companies typically do not have good understanding where the costs actually account for, from what sources. So this is the first step you can do. You start measuring what your devices do. You can start calibrating your routings, meaning that you get a statistical evaluation of how long the operation takes. Then you can start costing the labor more accurately. Thank you. And you can start accounting also for the energy costs. So it's not only about hitting the material cost right, but also about labor and energy. And not only electrical energy, but also it is about compressed air. Believe me, lots of companies lose significant amounts of money through unnecessary operations of compressors and through obsolete distribution of the compressed air throughout the plants. So that's another subject I encourage you to look at. And most of these machine tools actually do need compressed air for the operation because it's used for cleaning the machine part, for cleaning the tools, etc. And again, imagine that your machines are idling as much as you see at the bottom. The machine at the bottom looked like was operated for half of the time, but still your compressors are running. Then quarter of the time machine was just idle electrically. So your costs are just creeping on, and it's just creeping on.
And heating is still on.
Heating is on, compressors are on, exactly.
And by inefficient routing of the compressed air, you mean that there are some leaks?
There might be leaks, or there perhaps the piping is not sized up. You might have changes of pipe diameters. It works as a choke. You start losing energy, right?
Yeah.
Or the bends are not right. You know, the kind of interconnecting bends are, basically causing pressure leaks or pressure drops. So again, interesting. The modern compressors use actually waste heat recovery system because the air compression causes lots of heat to be developed. So you can recover it if you have it close to your boiler room. Again, I can go back to one of the previous slides. And imagine here the additional resource would be recovered heat from your compressor. You feed that heat to the buffer tank and distribute to the plant. So when you buy a new compressor, again, it's not only about the electrical efficiency. It's good to have an inverter-controlled compressor that can run variable speed. If you have on and off compressor, it causes significant spikes in a grid, and we will get to what it means in terms of 15 minutes spikes and how much it can cost your company. And this is what I've thought to discuss in terms of what it means when you do not optimize the technological process. And this is again a case study I've conducted with a medium-sized enterprise, and they operate a heat treatment facility because they process lots of steel that is then machined for a challenging application indeed. But essentially they do quenching and tempering that is separated by technology break. There are lots of burners that actually are kicked in at the beginning because you need to bring it to 920 degrees C so that you can start performing quenching and cementation. It's just to give you an illustration how energy demanding it is. And the hundreds of kilowatt of power consumptions are just ticking. The cycle on quenching easily takes a whole day, 24 hours in a row. And you run it at higher tens of kilowatt hours of natural gas supply, or hundreds even. They got several of such as devices. And we did a study so that the first batch was set only at 16% of nominal batch weight that can be plugged into the chamber of that furnace. And we fixed the quenching and cementing cycle the constant, and we repeat the same exercise with a different batch, again with the constant duration, but with 62% of the nominal theoretical limit of the furnace that you can plug in. And in overall, in the first case, to perform the quenching process, we spent 0.4 kilowatt hours per kilogram per hour. So it's like normalized energy spent. And in the second case, we spent only 0.1. And that's what I mean, that if you do not understand the actual energy spent, you cannot get the costing right. So you can see how they were getting the costing incorrectly. If I'm not mistaken, this thermal processing accounting, depending on what was the order and what was the production order, from 20 up to 30% of overall costs. And that's guys what I mean, that if you do not get these cost breakdowns right, You can be still wondering why I'm not hitting the margin, but here we go. So understand how much of material you spent and what grades of the material, understand the labor, understand the energies. So another interesting aspect in that company was that some of the batches were a bit of an eccentric shape. You know, you might have sort of some chunky piece of steel that you just plug in and you don't worry about it sort of changing its shape. Mm-hmm. But imagine that you have, for instance, a ring that has got a big diameter, and you need to plug it into that thermal processing device, and you need to use a jig so that you fix it in a position so that it doesn't twist. You know, some of these eccentric shapes can easily twist, and you would basically have to scrap it afterwards because you cannot maintain the dimensional tolerances. Okay, so then we again started digging deeper, and we discovered that in some of the cases, and this is not to criticize the company, it was just the historical way they've done it. In some cases, up to 80% of the batch weight, and again, the weight equals energy, as you can see on the left-hand side, was a ballast, a big jig that basically clamped the value-adding element that was undergoing the heat treatment. Mm-hmm. So again, one of the exercises and lesson learned was, how do we redesign the jigs so that the 80% of the batch load is not the ballast? Yeah. And we go back to the manufacturing technology and how do we design it. So I just want to point out that sometimes these are very complex exercises. Excuse me. And, you know, we have to do lots of measures across the whole company, from design through manufacturing technology. We have to change the bombs, the routings, and the whole way how these devices are operated so that we can reduce the energy. So some of the countermeasures are straightforward. We replace electric boiler with a heat pump. It's okay, we call a plumber and electrician, and it's done next week. But this thing will take a year to redesign. This is a certified industry, so they have to certify the individual technological steps. So not a trivial exercise for them at all.
But after that, they will get the proper cost, the energy cost for every product.
Indeed.
And without it, it's just guessing.
Yes, and they can optimize because they can optimize the batch size. Mm-hmm. And we optimize with the manufacturing director that in some cases, you know, it might not be optimal to do the heat treatment in-house. You know, it might be beneficial for them to actually outsource it because, you know, there are professional heat treatment plants. They have a variety of different quenching and tempering chambers. They can have an optimal chamber that fits the volume and mass of that particular batch. So sometimes it's good to see sort of multiple avenues how to achieve that saving that we are after. Interesting enough, we went further in that plant and we did like a decomposition of what happens with the heat that we develop in that hardening furnace. So we heat the batch. There's a convection and radiation out of the shell of the furnace. There's a stream of hot flue gases. So that basically goes to the ambient. There is an oil bath. So when you finish the cycle, you actually dip that very hot chunk of steel into oil so that you do the tempering. You relax the stress in the steel so that it gets a combination of hardness and toughness eventually. It's actually an interesting process after all. And there's also a salt bath in one of these devices. Part of the technology, you need to wash it to get rid of the salts. In one case, you bath it in oil, in another case, in a special salt liquid. So every time you can capture heat. And interestingly enough, since this plant actually runs 24/7 because you don't want to shut down these furnaces, you effectively get seasonally independent source of waste heat. And that's interesting, right? Because we've talked about that there might be issues in the winter with energy supplies, and suddenly you got lots of waste heat that you can capture. So for these different batch volumes, we calculated we can capture 14 to 70% of energy. So per every dose for every batch, we can save nearly 1,000 crowns. Additional 5% savings from the oil bath. And what it means that the company doesn't need to turn on the gas boilers unless it starts dropping below the freezing point. So we are getting to the desired state. We are discussing also replacing the compressors with the new kits that have got waste heat recovery. And bit is joining another bit so that you are becoming gradually energy independent. So I'm getting back to my quote of one of the customers. I got photovoltaics, I'm independent. Now I revert back to that quote. These guys are getting independent. They won't be fully independent because that's energy intense industry, but it's about small streams joining themselves at a confluence so that a big river of savings eventually appears.
Yeah, the savings on the other hand, and also the energy safety.
Yes, absolutely.
Reduction.
So bonus. So we've talked about 6 measures, and the bonus one is about reserved electrical power, and that's an interesting subject. So we talked about volatility of supplies, and especially in the winter time, that might be a very frequent need to supply what they call support services from the energy producers. So the support service means that the transmission grid operators calls up an energy producer that is actually listed and that had won an auction on a very short notice. So for instance, if you imagine you run a hydropower plant, you need to be able to phase in within 8 minutes and start supplying the full power that you've committed to provide to the transmission grid operator if required. But this energy is super expensive. For illustration, a couple of years ago, the transmission operator spent 2 billion Czech crowns annually on these support activities. Last year was 6. It is anticipated to go up to 50. So it tells you the magnitude of a problem that we lack the stable power supplies, because you have to supplement it by the cogeneration unit, combined natural gas power plants, all very expensive resources compared to coal or nuclear.
In 8 minutes, you need to start the process.
Yes. You need to be grid connected and provide full power.
The expectation is that it will be 20 times more higher. Because like you say, like, 2 billion per year, and
is heading up to 50 billion annually.
50.
What the operator will have to pay for these support services, and this will be spread again. Someone has to pay it, right? So the end consumers will pay it. So it's actually, I'm just kind of throwing in facts to support my claim that please be conscious about energy independence to the extent that is meaningful, and energy safety. So the company that I would like to discuss at this slide, as a big consumer, it is connected to the high voltage connection point at 22 kilovolts, right? It's not domestic connection point at 400/230 volts, but 22 kV. So they are obliged to actually measure what is the power consumption within 15-minute cycles. So what it does, you got these continuous electrical meter, and it starts measuring at 0000. It stops the first cycle at 0015. And then every 15 minutes, it actually integrates the energy spent within that 15-minute cycle, and then calculates by division by these 15 minutes what was the actual power drawn in these 15 minutes interval.
Average.
emerge. Exactly. And these guys have set the reserved power limit at 620 kilowatts. So I've asked the maintenance manager to actually send me an annual record that can be downloaded from the electrical meter. And as you can see, there were occurrences of on the right-hand side when they exceeded the 620 kilowatts reserved power limit. If you exceed that reserved power limit, you have to pay 4 times more per kilowatt than you would do below that limit. And what it does, the power supplier looks at the monthly record. They pick the occurrence with the greatest excessive consumption and say, okay, this month you have consumed 700 at the most. That means you are 80 kilowatts above your limit of 620. And these 80 kilowatts will be multiplied by 4 per the kilowatt rate. So it actually jumps up, what you pay eventually. So it is a trade-off in terms of how much of reserve power you book, because the booking of the power means you are telling the grid operator, okay, I might use that much of power, but you will be heavily penalized if you exceed. So you have to find the balance. So I calculated
how to set the limit.
Exactly. Yeah.
Okay.
So that's what we are going to elaborate. So as you can see, they had occurrences where they exceeded. So I calculated a mass probability function. So I analyzed the whole year span. I was provided with the raw data in terms of what were the 50 minutes peak spans, and it turned out that there was a 2.8% probability of exceeding the limit. So it doesn't look that big probability, but you see there were excesses up to 730 kilowatts. So quite significantly above the reserved power. You can see that it wasn't standard normal distribution, but it was a bit skewed. So I calculated the median, to mathematically interpret it correctly, the probabilities. And I did such analysis you see on the next slide. So I look at every month the data. So what was the peak power? So how much we exceeded the limit of 620? And the column at 620, that's the current limit. Okay, so it means that they paid more than 500,000 Czech crowns for spending more above that 620 limit. And then I did a sensitivity analysis. So if I increase the reserve power to 640, 660, etc., and as you can see, if I set it to 720, there was just 1 month when they exceeded. But okay, you can say, okay, well, I'm gonna exceed or increase the reserve power, so I never have a excess. But you have to pay for that reserved power capacity. And as in every other scenario, there is that rule of diminishing return. If you invest too much, it stops paying back. So you can see the charges for exceeding are the blue curve. The saving versus the reserve power, that's the gray curve, because we compared with the annual fee for the reserved capacity, which is the orange. So somehow at 700 kilowatts of reserve power, reserve capacity, that's the optimum for the company. And by doing so, they will save 300,000 every year. So
it's a lot of money.
Yeah, and it comes for nothing.
10,000 euros, right?
Or, yeah, even more. Yeah,
even more.
Yeah, it's like 12,000-13,000 euros. So you can buy a nice static energy storage for that.
That's true. And it's just you just changed the number.
Yes, exactly. Yes.
Reserving from the provider.
Yes. So it's a couple of clicks in your web portal.
Yeah, that's actually a very nice thing that the optimization can do such a change in your electricity bill. I think with the energy prices going up and up, it's going to be way more interesting than it was like 10 years ago, right?
Absolutely.
These optimization opportunities or projects weren't so exciting and they weren't so interesting.
Yeah, very much so, because the paradigm was okay. The gross power was traded for 30, 40, 50 euros at the megawatt per megawatt. Thank you. At the exchange in Leipzig, in Germany, it was very stable. Didn't fluctuate much. So there wasn't that pressing need, and there wasn't that good return on investment. But the return on investment, it is becoming very apparent. It is there. And well, in any case, please do the math before you commit to the investment. But there are some simple steps you can take that cost you virtually nothing, as tuning this reserve capacity. And by the way, if you start operating the fleet of electric vehicles, at least in Czech Republic, there are two methods how you can reserve the capacity. You can do it once a year, and it's valid for a whole year, or you can adjust it monthly. So if you have a big fleet of electric vehicles and you have photovoltaics plants, meaning also that the PV plant will help you in the summer, you are going to have a significantly lower consumption in summer. You can talk to your operator and say, okay, I want to have a monthly reserved capacity, unlike annual, because it will change by month. The reserved capacity will cost you somehow 15% more, but again, it helps you to leverage your photovoltaics most. So lots of you can do. So to conclude it, and you could have noticed that lots of the measures were applied for households as well as for enterprises. So I'll do the summary this way as well. Think about what is cost effective as the heating medium, especially for folks in Finland, in Czech Republic. Do not be dependent on single primary energy media, but have the plurality and freedom of choice what to switch should the volatility continue, and I think in many cases it will continue. Do not hesitate to spend a few more thousands or hundreds of euros to install the measurement devices so that you understand how the device behaves. It's actually interesting. My house is located near a river, and we've got a lot more humid climate than a colleague of mine that we compare notes with, and I get lots of significantly worse performance because there's lots more defrosting happening on my heat pump. It's interesting. Such a small nuance.
Just a river.
Just a river
nearby.
A different microclimate. So my heat pump has to do a lot more of defrost operation, by the way. Think about photovoltaics. If you call up a supplier of photovoltaics, I want to have photovoltaics. The interest of a photovoltaics provider is to install you as much as possible. Okay, your roof can handle so much, go for it. Well, it might not be optimal investment for you. So it's worth to think about it. Also from a perspective of the static energy storage. I don't see much of need to have big storages that cover 2 days of your consumption. If there is some sort of blackout, it might happen in the future. Let's have it as a overnight source. If you have big photovoltaics, let's have it as a UPS for a couple of hours. That's okay. Why to spend more? If the prices go down in the future, you can buy more. They're modular static storages, but you don't have to basically spend your annual capex just for sake of having big, fabulous energy storage.
And actually, you mentioned the blackout. Do you think that we are going to see more blackouts in the future, or it will be the same?
There were multiple notes about grids being on the verge of, you can call it consumption rationalization in Western Europe, because France had big problems with operating the nuclear power plants. Roughly 50% of blocks were down in December last year. There were issues with grid stability in Britain, recorded last winter. This winter, still Germans operated 3 nuclear power plants. All of them will be shut, or have been shut actually recently. So these issues are getting pronounced. There are also questions to what extent the underground gas storages will be filled for next winter. So I'm not saying it is going to happen next winter, but the decarbonization is picking up pace, and there is no means of subsidizing these unplugged resources. And on the enterprise level, I'll repeat myself a bit. Be conscious how much you invest into photovoltaic plants, what is the big story behind it, and understand what's happening in your plant. Measure it, evaluate, and use the data for savings. Optimize the technology, optimize your production plan, optimize, how much of reserved capacity you have. And these small bits will make a big effect in turn, both in terms of energy independence, in terms of energy safety, in terms of understanding your costs, in terms of saving the costs. And in turn, your business will flourish, certainly, using these measures. So that's my encouragement. You might think, okay, it's beginning of spring, so why to worry now? I say, contrary to that, you still have a whole summer and autumn season to conduct measures, yes, and implement any investments needed.
All right, thank you very much, Erik.
With pleasure.
Are there any questions from the online audience, or some comments? Something it was surprising for you, something new you learned, you heard? Actually, if there are no questions, I think we've filled the topic. That's actually everything from us for today. Thank you, Erik, again, very much for sharing your experiences, how we can save money on energy cost, not only for households, but also for enterprises, small and medium, and what it means for energy safety and the future, and product prices calculations and so on, because these topics are going to be way more important than they were before.
So thank you for hosting me. It was a great pleasure, and I would encourage my listeners to find me on LinkedIn. I publish weekly news and experiences from my consultancy cases, so you can keep on following me and seek inspiration at my profile. Thank you.
All right. Thank you as well. Bye-bye.
Bye-bye.